What is up, everybody? Welcome to Elasmocast. My name is Ben Goode, and today we have a very special guest. We have paleontologist Jim Kirkland. How are you doing today?
I'm doing well. It's been a busy day, New stegosaurs being sold off at Sotheby's, and dealing with getting our dig site opened up, find some new dinosaurs. It's always something, no
Yeah.
doubt about it. But as state paleontologist of Utah, I've been pretty lucky to work in this region, the southwestern U.S. and Mexico, for 51 field seasons now, and been keeping pretty busy. And really, where I started was marine Cretaceous, graduate school. But I started, I had an interest in dinosaurs, but I even was thinking of going into trilobites when I first started into grad school. But I love dinosaurs. I think there's no future in it. We're talking back in the 70s,
Mm.
where a job in dinosaur paleo, maybe one job would appear every couple years. It's a little better than that now. But back then, I figured I might want to have a family someday. But what got my foot in the door, I'd been working on marine Cretaceous ammonites, inoceramid bivalves, the Black Mesa Basin, and Mogollon Rim on the Apache Reservation, and working in the Hopi, Mesa area. Got to know the marine Cretaceous in that part of the world, San Juan Basin, pretty well. Um, and colleagues are starting to work in southern Utah on the terrestrial Cretaceous and what's now Grand Staircase. This is well before there was a Grand Staircase, Escalante National Monument. And they were screen washing sites looking for mammals. And, look at this stuff with them and say, man, you're finding all these fish teeth and shark teeth, freshwater sharks. Who's working on that stuff? They're like, oh, who cares about fish? You got people interested in dinosaurs, the mammals who are paying the bills, lizards, but no one's working on fish. So I started working on, the freshwater fish assemblages, and really started working seriously on freshwater elasmobranchs, looking at these things, and pretty diverse assemblage. And the microvertebrate sites they were developing in southern Utah basically spanned every single substage of the entire Upper Cretaceous. So not just Cenomanian, Turonian, lower Cenomanian, middle Cenomanian, upper Cenomanian, lower Turonian, all the way through, all the way up into the Maastrichtian before the extinction. So I got to really get familiar with these assemblages. And one of the things about the late Cretaceous freshwater, elasmobranch assemblages in the West is heck, there's always about 5 taxa. There's 2 big lines of freshwater hybodont sharks, holdovers from the Jurassic and Triassic. These little ones, in the group of Lysotis, and in the Upper Cretaceous, Longidian, as the main taxa that we see through these rocks. And then, of course, the bigger hybodont sharks with, big, more ornate fin spines. Longidian also has fin spines, but they're much simpler, smooth little spines. And they're fish, that are maximum, couple foot long max, where hybodont sharks may be getting as much as, 2-3 meters, probably 3 meters, and probably a good sized hybodont shark, with, dorsal fin spines, and, are getting close to a foot long on the very biggest ones. And these things are probably in the big estuaries, big rivers, but we also get, a lineage of freshwater rays, the myelodaphine rays, which I've been interested in from the start. They started realizing there's different species here. This is not all Myelodaphus bipartidus, the Cope name back in the 1870s. There's a number of different taxa at different levels. And I've worked quite a bit on that lineage, sorting it out. But there's also rectolobids, carpet sharks, and scilorhynchid, more derived neo-Silesian type thing, carcharodid sharks. But these little carcharoidids And rectalobids are all about, a foot long. These are small fish with teeth that are a millimeter, 2 millimeters across. But generally, you say for most of, particularly the latter half of the Upper Cretaceous, freshwater representatives of both of those lines appearing and evolving within these river systems. And then there's one of my favorite groups of all time. We get freshwater saw skates, scalorhynchid pseudo sawfish. And the ones we see in freshwater environments are pretty small taxa and have minute oral teeth, and also pretty minute rostral barbs going down their saw blade. In fact, one line, the tychotrigonids, that are more of a marine line than the iscorhizid texatrigonid things that I've been working on. Those things have probably completely lost the rostral teeth and have developed more of just a smooth bill, I'm figuring, on the saw. But the texitrigons have teeth that are obviously tychotrigonid style oral teeth. But these lines, there's always 5 or 6 freshwater elasmobranchs in every sample. These microsites. And people, freshwater sharks. I'm in Utah, so they don't know a lot about elasmobranchs here in general. But basically, if you go to Australia, the Fitzroy River, there's 5 taxa of freshwater elasmobranch in the Fitzroy River. You got freshwater sawfish, freshwater rays, kind of freshwater sharks, all in the Fitzroy River and going miles inland, way inland on those rivers. And you get 5 taxa of modern freshwater elasmobranch way up those river systems. So it's just in North America, we don't see a lot of sharks go way up into our rivers anymore. You don't see them up in the Mississippi, none in Ohio that I know of. But pretty much elsewhere in the world, things were, freshwater elasmobranchs were operating like that. We have freshwater elasmobranch rays and things in the Amazon and, many of the rivers in Central Asia. As I said, Australia, Mekong Delta, things go way up into Southern Asia. So freshwater elasmobranchs are part of our modern shark assemblages, ray assemblages, but not something that's thought about all that much. It's pretty neat. I've really enjoyed working on that stuff, and I don't have to worry about anyone selling my sawfish off for $44 million. I mean, people shoot people for that stuff. It's like, okay, yeah, like, let's keep the numbers down on this.
Yeah.
Yeah, little tiny freshwater shark teeth. Yeah, you're safe with that. It's just the bean counter is worrying about permits. It's a vertebrate. Got to have a permit. No one would care at all. We'd be able to do whatever we wanted. Compared to dinosaurs or large mammals and things of that sort.
Yeah, sharks are kind of like the bystanders with all of these laws, especially here in the Southwest. Like in Arizona, you can't collect vertebrate fossils on public lands and state lands, all of that stuff. But in reality, those things are meant to protect the dinosaurs. Like we have Dilophosaurus here, we have Coelophysis and stuff in the Chinle, but they're not caring about these Mississippian age halocephalin teeth. So
Yeah.
they're still, vertebrates, so we still have the protection
Apply
on.
for a permit. I want to
Yeah.
collect some, Mississippian age elasmobranchs, and they don't know what to do. Because it's just, this is totally different.
Mhm.
And shark teeth. I always loved before they even had PERPA, before the Paleo Resource Protection Act went through, the little brochure the BLM had for collecting fossils on public lands. There's a note: you can't collect any fossils, vertebrate fossils on public land without a permit, because that's always been the rule, or virtually always been the rule. And it had this little statement, and that includes shark teeth. This little subline, because everyone thinks shark teeth are fair game. It's like they're not. You have to have a permit to pick up shark teeth on public land, and it's it's one of the great things the public should be able to get involved with, because there's more eyes out there, the public. As the state paleontologist of Utah, I really do think we need the public to be part of the team. Let's all
Yeah.
work together on this stuff. And, I think the public should be able to write scientific papers, should be involved with our various dig projects
Hmm.
as well, because the public loves this stuff. That's why I have a job, that the public loves this stuff. And, as you know, with the Elasmobranchs, there's so much we don't know.
Hmm.
People, oh, we know all that stuff. Hey, say about dinosaurs. When I started this job, there were like 25 dinosaurs known, by name in Utah. Now we have well over 100. The last 30 years, we've got well over 100 new ones.
Yeah.
This is the good old days. And people have largely ignored, the marine faunas of Utah. And I will guarantee you that there's, the are in southern Utah that started to produce. People haven't even looked at them in central Utah yet.
Hmm.
I mean, this is, virgin territory with
Yeah.
hundreds of square miles of outcrop.
Yeah. And the thing is, too, like these fossils that are out and about, if people don't pick them up, then a lot of times they'll just weather away because, especially here in Arizona, we have super strong sun. So that's going to bleach and erode away the fossils. So if they don't get picked up, then they become dust. And also,
Yeah,
the little kids that find this little fossil or something like that, even if it might not be super scientifically important, them taking it home could literally lead to them pursuing a career in dinosaurs or sharks or anything like that.
absolutely.
Generation.
Yeah, I mean, I always talk about dinosaur paleontology, but shark teeth is the same thing. These this paleontology, vertebrate paleo in particular, paleontology in general, it's a gateway science. It gets kids interested in fossils. I mean, I've worked on the Big Res, the Navajo Reservation, the Apache Reservation, the Hopi Reservation,
Mm.
for years, 13 years of my life is intense on reservations,
Yeah.
working in the Manco Shale or the Mogollon Rim country. And basically, at camp, we have Navajo kids coming out because, who are these guys out there,
Hmm.
Uh, and they come out and join our camp and play frisbee. But also, I'd show them, this is how you find shark teeth in anthills,
Hmm.
and Lepidotes teeth, in the Natarita, which you guys call Dakota down there, I think. Still, we've dropped Dakota because it's not the same thing. But these little Lepidotes teeth, they're like already ready to set the jewelry. These kids are like, what is it? I go, yeah, it's a fish related to a gar. What's a gar?
Yeah.
It's starting at ground zero, but they know these are fossils. They find a shark tooth. Ooh, that's neat. And just watching these little kids, light up, finding these things is a lot of fun.
Yeah.
And I really do. I think the tribe should try to take advantage of that early wonder kids have about these, dragons and sea monsters and things, that are so unlike, anything they see around them normally. It just opens their imaginations.
Yeah.
We need to take advantage of it. We got to move into the future and bring everybody with us.
Hmm. Yeah, I mean, you have a lot of people that get their start like me watching all of the shows like Walking with Dinosaurs and Chased by Dinosaurs and stuff like that. But then there's another group of people that really get their passion from finding that first thing on the field, just like stumbling across a fossil, and that just sparks everything for them. And then they go down all of these different rabbit holes and all of
Yeah, I
that.
remember when I first, I grew up in New England,
Me
the
too.
South Shore, and I got to collect fossils down in Narragansett Bay. With my earth science teacher, took me
Hmm.
to a few sites because he knew I was pretty passionate about it. I mean, my biggest release was running up to Cambridge and going to the Museum of Comparative Zoology at Harvard and staring at the Chronosaurus. Like, someday I'm going to collect me something like this, and I've done okay. But going down collecting those fossils, go to New Mexico, I knew nothing. to go out in the marine Cretaceous. First place I went to look for fossils at Carthage, New Mexico. And one of the first things I got really excited about was a bunch of Ophiomorphas, which are or shrimp burrows,
Mm-hmm.
and they're covered with little pellets, and they were branching. And as the neophyte I was at 18, I thought I found a giant starfish. And there was Ophiomorpha burrows. I also found a couple nice ammonites. I knew what the ammonites were. But this thing is, this starfish, and it's,
Mm-hmm.
but I got so excited about this stuff. And, I was excited about paleo before, but going to college where I could go out and find really good things was really, life changing.
Yeah.
And I was fortunate enough to get on my first dinosaur dig in April of 1973. My first freshman year, got up the San Juan Basin, and it's been over 50 years that I've been chasing dinosaurs. But
Mm-hmm.
I've fortunately loved everything. I did my PhD on ammonites and marine fossils, figuring I'd never get a job doing dinosaurs,
Mm-hmm.
and got my foot in the door working, as I said, got my foot in the door in vertebrate paleo. But, well, I'll look at the fish if no one else will. And that opened up the door, and I still love this stuff.
Mm-hmm.
I think one of my biggest discoveries was when I found with Martha Carolina down in Mexico, the first blades articulated rostra of Schizorrhiza. Schizorrhiza, I want to name the paper the ultimate sawfish, because these scleroranchid pseudo sawfish or saw skates, which I do like the term saw skates, they're not related to modern sawfish or saw sharks. It's another independent radiation that went extinct with the dinosaurs. Got them right up to the meteor impact, which I've also worked on. Right up to the impact, boom, they're all gone. Mass extinction of Elasmobranchs at the end of the Cretaceous, very underappreciated by most folks, but all the scleroranchids went out then. And Schizorrhiza lived at the end of the Cretaceous, and they have these triangular teeth that form a dental battery of overlapping triangles. So it actually forms a saw blade around the rostrum of these, complex interfingering blade-like triangles along the edge of it. So literally, if this was the South Seas today and these things were fresh, you chop one off, you could saw, with those things, no question about it. These were a very effective, slashing blade. And these are clearly not grubbing in the mud. A lot of sawfish use the prongs, come up the saw to, pull earthworms, sea worms, and other, burrowing invertebrates out of the sediment, stir up fish so I can just grab them. This thing is slashing that bill, probably like swordfish or other billfish today, swimming in schools of fish and slashing that saw blade back and forth, hacking the fish, and then just swimming back through and picking up all the wounded and dead fish that they've trashed with this beautiful saw that they'd evolved with over tens of millions of years. This group comes in probably the early Cretaceous and really diversifies into a number of lines, doing very different things. Look at Onchopristes, in the Cenomanian, North Africa. I collect Onchopristes in Black Mesa. They're little tiny little barbed rostral teeth. They're about that big, but half a centimeter really is about the size. I've never seen one a centimeter big at Black Mesa ever in my life. And then you go down there and you're seeing them 5 and 6 inches long in North Africa, representing sawfish that are on the order of 5 meters, for the big ones. And they've got a Spinosaurus, that is an Onchopristes tooth embedded in the jaw. So there is no question Spinosaurus was taking these fish on. They probably were, shallow coastal, giant sawfish. But these giant fish-eating dinosaurs had giant lungfish. They were probably 2 to 3 meters long, living in those coastal estuary environments. they had these fish called lepidotes, or Shinsia is the name they use now for the Cretaceous ones. But
Hmm.
these huge semi-anodid armored fish related to gar. And if
Yeah.
your listeners know gars with their big enameloid diamond-shaped scales, these things are more bass-shaped, you could think of.
Mhm.
But a big lepidotid, semi-anodid, they can get to 2 meters long in these environments. We see scales, like that big around at Black Mesa, because in the Natarita Formation, or Dakota, as they call it down there, these were like salmon. They're living in the marine realm, but they were going way up these rivers, probably to reproduce.
Hmm.
And I'm still waiting for us to find a spinosaur, in those rocks at the base of that marine sequence, because all the spinosaurs apparently go extinct with that Cenomanian extinction, as do these giant semi-anodids that were, this major coastal fish. And we know the wear on these teeth, because you're biting through chainmail, enamel on enamel. You can cut a diamond with a diamond. Well, enamel would wear the enamel on the teeth. So if you look at spinosaur teeth, and we see this in Dilophosaurus relatives, the carina, these big long teeth get worn from the root all the way to the tip, front and back. And that's because these things were taking advantage of these armored fish in these lake sequences, probably, for Dilophosaurus when they're reproducing. And when they bite through this chainmail, it would wear these teeth in this really distinctive wear pattern.
Hmm.
We see in the early Jurassic of the Colorado Plateau region, and we see in North Africa with the Spinosaurs feeding on all these, big giants, saw skates,
Hmm.
lungfish, and these lepidotids. I mean, it's, dinosaurs, Spinosaurs really moved into that realm. The Cenomanian, Turonian extinction, did them in, and dinosaurs never really got into a major fish eating role ever again. It's pretty interesting. What would have happened if the Spinosaurs hadn't been killed off? We had big seagoing dinosaurs going after fish. They just didn't cross that line ever, and heck, barely made it, into something that would be taking out coastal, large, marine fish.
Hmm.
And they did. There's no question. Dinosaurs were interacting with those giant sawfish, which is pretty cool.
And that area in North Africa, was a lot of that also freshwater environments too, with those.
Yeah, you had estuarine environments, because we get dinosaurs and
Mhm.
what is it, Deltadromeus and Oranosaurus, and there are a variety of dinosaurs. What is it? Poseidon, Poseidon, Titan. I can't remember that big sauropod that they
Mhm.
found in Egypt in those rocks. But you have all these animals that were clearly living on land, and spinosaurs were in those environments too. So
Mhm.
out to the sea, there you probably had all these big estuaries. Look at the east coast of the U.S. Look at the Nile Delta, deltas and big riverine estuary environments. So you have that interaction between the marine and the freshwater. And as we see in Utah, a lot of those fish were moving up into these rivers, probably just like salmon do. And the sharks, they probably have, still maintained their ties to the ocean,
Mhm.
because we do see some lacustrine pond deposits that don't have sharks in them. I mean, the Mylodapine rays, we got the lineage going right back into the late early Cretaceous in central Texas. And they're basically guitar fish that
Mhm.
start developing a broad little tooth and develop eventually a nice mosaic pattern like the myliobatids do, of big flat grinding teeth and forming big tooth plates for doing in mollusks. But that group started off with a dentition like a guitar fish, these little tiny denticles, rasping things more than, certainly not built for grinding up tough, shelled organisms.
Yeah.
But we see that in the marine realm going in, and we see it in this freshwater line that goes all the way to Lake Cretaceous. And the Lake Cretaceous, there's Mylodapid teeth teeth, the Myelodapus pustulosus, they're as big as the end of my thumb in the individual teeth and the tooth plates. And those are probably 15 foot, guitar fish shaped, rays. They're not stingrays. A lot of people used to always say, oh, they're stingrays. No, they're not. They're convergent on them, and they come out independently, like the saw skates. We come independently, making sawfish out of early rays. We develop stingray type grinding dentitions independently out of guitarfish as well.
Yeah.
These things, radiated, tried new things. So I really developed a real love for these things. And with the Myelodaphid line, every stage, at least, in some cases substage, we see pretty big turnover. So we can identify the species based on crown ornament on the side, how well the teeth are packed. So we can see this complete lineage going from little round, completely isolated from each other teeth to these hexagonal packed teeth with striations down the side that interlocked. The last one's pustulosis in the late Maastrichtian, in the Hell Creek. Those things, those teeth are every bit as good as Myelodapus. Myliabatis today, or the eagle rays, the bat rays and the eagle rays. Those things are efficient dental, crushing batteries. That happened independently in these groups, and they're mostly freshwater. We start to see some groups, that doing the moraine. They never got in the Cretaceous quite as good as doing it as they did in freshwater, but they were heading that way before the extinction. We start getting a thing called rhombotus, the end of the Maastrichtian, and they start getting a little more diamond-shaped little plate-like teeth that interlocked, actually tongue and grooved with each other front to back, as well as interlocking these little diamonds. And probably a pretty good crushing battery. That whole line extinct at the end of the Cretaceous with the saw sharks. People just don't realize, how big the extinction was. And it was bigger actually on the ray groups. They were really trying some things than it was on the sharks. But the shark groups, had a major extinction as well. There at the end of the Cretaceous.
One
It
of the
wasn't
biggest
just
ones.
dinosaurs.
Yeah, one of the biggest ones are the hybodonts that were around all the way back in the Paleozoic.
Yeah.
And and that's one of the groups that really found that niche earlier on as far as going into these freshwater environments. Like you said
Yeah,
before,
absolutely.
yeah, with Lysotus and Lonchidian. And those were for the most part small animals. They weren't
Oh,
these
yeah.
massive things. Like in the Paleozoic, we would see like Orthocanthus in the freshwater, which would have been these much larger animals. But for the most part, in the Cretaceous, we see a lot of smaller hybodonts. Hybodonts really, they didn't become extinct until the late Cretaceous, but their diversity definitely diminished down because in the marine environments, as far as in the US, we see some Marastodonoides teeth, but we see nowhere near the same quantity of hybridont material as we do the neoscellation material.
And for the Trias and Jurassic, particularly Triassic, they're dominant sharks.
Yeah.
Sharks almost went extinct at the end of the Paleozoic. They barely squeaked by. Neoscalations, I worked I used to teach at the University of Nebraska
Hmm.
for a few years after, my graduate school work at Colorado. And, I did micro paleo stuff at Peru, Nebraska, on the Penn Perm boundary assemblages there. And, we've got hybodont sharks and, a nice variety of little cladodont sharks, teeth and amphibians, and you even find eurypterids, little eurypterids. At the base of the Permian in these estuarine rocks, a last gasp for that group. But one of the things we see in there that I found, because I was screening in small screens like they use for foraminifera,
Hmm.
these real fine mesh screens, set sieve screens. And basically, I was getting neoscellation teeth in the Penn Perm beds. And those teeth were like a millimeter across. They were tiny. I got 20 or so of these, and it's still never been published. I think Adam Hunlocker's got that collection now with them at Southern California University, like Permian, Penn Perm stuff. But these tiny neosalations, those things were under a foot, or no more than a foot long,
Yeah.
and they're in these estuarine, environments, maybe going into fresh water, but literally they're like trout size. And these are neosalations, the
Yeah.
sharks that gave rise to all our modern groups.
Hmm.
And they're like, little tiny things with tiny teeth. They're diagnostically neosalation teeth.
Yeah.
But these are the ones that survived through that stuff to the end. And even through the Triassic, they probably didn't do much, till they
Yeah.
started get bigger in the Jurassic.
Mhm.
It took a long time. Whenever people say sharks, or living fossils, I just laugh because modern sharks are a modern group.
Yeah.
So, well, what about hammerheads? So hammerheads been around 15 million years. They're recent as can be.
Mhm.
They've been around almost like hominoids. Or they're as old as our group. I mean, literally, like, yeah, hammerheads came up with early man.
Mhm. Yeah, and when people see publications that say like Carcharias taurus has been around since the Cretaceous or whatever, or you the
Yeah.
genus Extinctus in the early Jurassic, a lot of that is just remnants from old publications that weren't able to distinguish it, but nobody
Oh
just
yeah.
actually went back to revise these things. So it doesn't mean that these sharks have been around that long. It just means that back in the day, when paleontologists didn't have as much to work with, they gave these diagnoses of them, but they just nobody wound up
Oh yeah.
correcting.
In early papers, they're putting all these sharks. I mean, we talk Cretoxyrhina,
Hmm.
but that was Oxyrhina originally. They're making
Yeah.
it a mako shark. Those early papers by Louis Agassiz and stuff.
Hmm.
Those things are they didn't know enough, and of course the earliest saw skates, they were Oncopristes, Pristids. So we get all these names like Oncopristes is like they have nothing to do with Pristis, so it's a
And
completely independent line.
to be fair, I mean, with what they had working with us,
Oh yeah, I mean,
so the odds of convergently evolving a sawfish-like rostrum with those bladed rostrums, that is such an unlikely thing that we came to later find out that happened three separate times within Elasmobranchs
separate
at least.
times, yeah. And it may have happened more than once in the Cretaceous.
Yeah,
I've talked to some people that think Scorinchids may be polyphyletic and not a natural group, but
it's
you know,
crazy.
I'm too late in my career to delve into that one at this point. But stuff is not impossible. It's but we do have lines that survive. Scapanorhynchus, is virtually. I don't see how you tell it from a modern goblin shark. Why are they a different genus than the modern goblin shark? Was it Ginkliostoma, something like that?
Mitsukarina.
Oh, Miscarina, yeah. Miscarina, how does that differ? I mean, we got Scapanorhynchids in Lebanon that are like flawlessly preserved, and they, are clearly the same kind of thing. It's like, okay, how do they differ? And is that difference really a generic difference? But generally, there's almost nothing, in the Cretaceous that should be considered to be a direct line to modern stuff.
Yeah.
Cretotus made it almost. Yeah, it got close. But should Cretotus megalodon be in Cretotus? I mean, that thing's bounced all over the place.
Hmm.
Carcharodon, Carcharocles, uh, um,
Megaslacus.
yeah, what is it? Orotus, not Orotus,
Ototus.
Ototus.
Yeah.
Ototus. I mean, that's had 6 names in the last 20 years. Once they finally came around and said, oh, Carcharodon comes out of a mako. Ocelus, it
Hmm.
has nothing to do with Carcharodon, and that line, just once again, convergence.
I
You
find
know,
that interesting that they thought that they were similar because in the same deposits you'd find the megalodon teeth. You'd find these clearly carcharodon-like teeth that just don't have serrations in all the same deposits.
well, no, well, these are Makos, you
Hmm.
know, and they put that in a new gene. It's not what's the right?
Cosmopolitotus.
Yeah.
It's a carcharodon.
Oh yeah, it
You'd
is. It
have a
just looks
paraphile
crazy.
if you have Cosmopolitotus just going into carcharodon. So
Yeah,
you,
absolutely. Yeah, Baja, they have populations that are just obviously that gene hadn't been completely fully dominant in those populations, which makes it really tough. Cladistics,
yeah.
everything's branching points, but populations can evolve. You know,
Mm.
I mean, it's like it is possible. And I'm a big believer in reticulate evolution. When things are good, the gene pool just diversifies because everybody lives,
Mhm.
and so you're gonna have mutations and they just go to the gene pool. So the genetic diversity of your population expands when things are great. Then all of
Mhm.
a sudden there's an environmental crisis. Is it drought, major, decades long continental drought? Is it, a volcanic thing going off, asteroid, basin gets cut off and gets stagnant. What happens? Who knows?
Mhm.
But you've got an environmental perturbation, and whatever that perturbation is, it helps hone what genes actually are positively traded. Evolution works mostly in crises,
Yeah.
and that crises may push it one way. A different kind of crises could push it another way, and
Mhm.
if you don't, separate these populations through these crises enough, then they might hybridize, just go break back together. And, when times are good, and that's why we call it reticulate. And eventually things split off so they can't reproduce again
Yeah.
and go their merry way, in separate isolation. But, I think that's, it fits the punctuated equilibrium view.
Mhm.
But, phylogenetics, the stuff that, we're getting crammed down our throats today, you can't have things hybridize. You can't have a separate branch come together and reproduce.
Yeah,
That just mathematics just disintegrate if you do it that way.
I mean, if you think about it, though, paraphiles are a natural phenomenon because, like you said before, you'd have a species, and then if a certain population gets segregated, then they'll wind up evolving at a faster rate, and they'll become a a different, I guess, species. Even though species are like a man-made concept, but still they'd speciate, while the other group that's populating in this much
Sure.
area will be a lot slower to
Oh
evolve.
yeah, you pinch these things off, and we have an expand like the seaway, in
Mhm.
Western Ontario. You expand that seaway, then you have a Chrysler, the seaway retracts, and then you have isolated section bodies of water, different temperature regimes, oxygen regimes, and you get somewhat separate populations that are adapted to those environments. And sometimes it's a totally isolated little, Hudson Bay little, group that totally stays separate for a long time. But when they reconnect, can they interbreed yet? Or have they become behaviorally so they'll never interbreed? Or the look, the ornament on the animal. Oh,
Mhm.
these yellow weird sharks and the blue ones. You're yellow. I'm not going to go near you. You're but they genetically could physically interbreed if you create a situation where they could hybridize,
Mhm.
kind of force them together. I mean, evolution is way more complicated than math that make good mathematical models. We just
Yeah.
always have to keep that in mind. A hybrid, fluke, you pull a little population and another one together, and they hybridize. The new result of that may have vigor and traits that are really good.
Yeah.
We always talk about hybrid vigor, and and then all of a sudden, boom, the thing that's the most robust grows faster, jumps higher, you know, twice
Yeah.
as.
And
But
you see even in modern zoology, they've found hybrid sharks where I believe one was a black tip hybridized with an Australian black tip. But the thing is, how we tell apart them is things like vertebrae count and genetics. There isn't really anything like we can physically differentiate, but then like is that a hybrid or is that just our classification of what a species is being different than
Well, and
me?
this is the thing when you're dealing with shark teeth.
Hmm.
You're looking at such a small piece of the hypodime. You know, I mean, basically the whole thing with phylogenetics is we're trying to take the phenotype, the physical expression of the genes and use it to get at the genetic. Because if you got chromosomes, you can do some really good phylogenetic work because you look at the chromosomes. Okay, this is when how they split. We can tell when they split. But if you're looking at just a physical object, you're looking at a minor. You're looking at the hard parts,
Hmm.
the color patterns. A lot of times species are separate because of color patterns or features that don't fossilize. Field crickets. You have a field with like 50 different species of field crickets. They're all black crickets, but they have different songs, in terms of the style of song.
Hmm.
They reproduce at different times of the year from each other. They have different shape, lock and key reproductive structures, so they can't physically mate no matter how much they try. I mean, you end up with this incredible diversity of field crickets, but superficially, unless you know what's going on, they all look like big black field crickets. Yeah. And these are some of the things that were found early on, in the last century, that, yeah, basically we can have populations with sympatric species, that don't interbreed, because they just behaviorally aren't going to do it,
Yeah.
or, the reproductive lock and key. That's unlikely to be preserved in the fossil record. So we're not going to know that those things that superficially look nearly identical can't even physically reproduce.
Yeah.
Yeah.
And the thing with
So
teeth
we
too.
know, you got to always keep in mind we're only approaching it,
Yeah.
and we've got to be careful and keep our minds open that we could be completely wrong.
Yeah. And as much as we love teeth and how diagnostic they are with elasmobranchs, the
Oh
thing
yeah.
is, like, good luck identifying a modern squatina based on its tooth.
Oh
Because you
yeah.
have all of these sharks, like squatinas, and you have even some carcharinids, they have so much. I guess with squatina, the teeth are so similar that when you factor in like individual variation,
Oh
you're
yeah.
not going to be able to identify it on a species level. And then with like carcharinids, they have some significant differences in morphology based on things like individual variation or where they're located, where their population is. So like the Indo-Pacific bull shark teeth are a little bit different than the ones that we find over here. So you have
Sure.
so many different things that in the fossil record, we don't really have the ability to tell apart these things. So we group them based on like say the geological formation and time that they lived, or we just assume that these are either the same species or different or whatever. But we can't know for certain with any of this stuff.
I'm really glad the Carcharinids didn't get too crazy, before the end of the Cretaceous, because Carcharinids, have some dang similar looking teeth superficially. It's like, okay, it's not, you're not going to tell, Cretoxyrhina, Cretolamna, you know, Dicotis, Squalicorax, Scapanorhynchus. All of those things are vastly different from each other. But a
Mhm.
lot of assemblages, if you're looking at, a Miocene, shark assemblage, go to Bakersfield and screen watch that stuff. You can have quite a diversity of Carcharidids. And it's
Mhm.
okay, we're just gonna, keep it to these simple morphotypes and
Yeah.
give them some names and make it, and that's good. We're making it good.
And there's even like
That's how you
sexual
do it. And this,
dimorphism. Huh?
uh,
Oh,
yeah,
I was
I
just
mean,
gonna
they
say,
really are the morphology. Lemon shark versus a bull shark, superficial, or even a hammerhead. These little recurved serrated teeth. I mean, you can tell them apart, but for the average person, these are really tough.
Yeah.
the tease apart compared to a lot of the Cretaceous things where, the lines, within each lineage, Cockoroids are a very diverse group today. Yeah.
Yeah. And like
Uh,
with the hard-nosed shark, Carcharodontis macloti, you have sexual dimorphism where the males have different shaped teeth than the females. And in the fossil record, unless you find articulated body fossils of both, you're not going to be able to tell that.
oh, yeah, no, absolutely not. And it's getting old. Tychotus, for much of my career, I was just convinced Tychotus was a specialized hybodont shark.
Hmm.
Now we know they're lamnids.
Yeah.
Absolutely. And they're big. I mean, these things were getting more than 10 meters.
Hmm.
Mort and I, we know these things these are some of the biggest sharks that ever lived, eating giant clams, these giant platycermus clams on the seafloor.
Hmm.
But those things, till we had whole ones with vertebral column, first vertebra was like, oh, these are certainly hybodont sharks do not have calcified vertebrae.
Yeah.
So they can't be hybodont sharks, you know. But who are they? And they're a little flatter than typical sharks, that you're getting at that time. Okay, so what group are they? And of course, now in northern Mexico, they've got bunches of complete. I mean, northern Mexico sites that have barely been worked.
Hmm.
They've got 5 or 6 good Tychotids, including some big ones that are complete, show the body outline, the whole bit. And these are big lamnid sharks that have become specialized, clam eaters.
Hmm.
And they are lamnidae, they are lamnid sharks, which absolutely, there's no question. They're just their own group. And what is there now? 21, 22 species. They still put pretty much every one of them as Tychotus.
Yeah, well,
Uh,
Tychotus is kind of like an equivalent to Carcharodontis, where you have this one genus that has all of these different types of teeth, and then you can have some like intermediate morphologies where like this Tychotus has a trait like this one, but it also has a trait like this one. So is it its own species? Is it a
uh,
hybrid? Is it just an
well,
in?
a lot of them, the teeth are pretty straightforward.
Hmm.
Compared, Carcharodontis, you got a lot of species, but the teeth are pretty similar to each other.
Hmm.
Tychotids developed some real, specialized grinding patterns, the ridge patterns on
Hmm.
the teeth are typically pretty distinctive. But almost anything with these groups, one tooth, I would not name a new taxon under any conditions of any of them. You know, I mean, there's people have tried to name pathologic teeth. It's like I think this thing got whacked in the mouth.
Yeah, I've had conversations with people about this tooth called, I think it's Eoscymnus, and they basically named it because it had this really distinctive root morphology. And what was weird about, so they called it a squalomorph or a squaliform shark. But the thing is, I have teeth of Ceratolamna maricana where they're completely, diagnostic as that, but with the root pathology that creates the exact same tooth-based pattern as Eoscymnus. And then I also saw at the Tucson Fossil Show a Jaculatotus tooth, which is clearly Jaculatotus with that pattern as well. So it turns out that that is a pathology that can be shared in common with several different lamniform sharks.
Yeah, keep you very entertained. One thing you might want to try um, is on some of these Paleozoic sites, try to find potential screen wash sites so
Hmm.
you can produce the assemblage. The stuff in Peru, Nebraska, which is a railroad cut, and the productive level is about maybe an inch thick, a couple centimeters thick, and so you got to just between sandstones, big sandstone beds. So you've got to really dig in, but it's incredibly rich and diverse. You get acanthodian tooth whorls, amphibian pieces, and sharks, and it's just amazingly diverse. Everything in that estuary environment is all there. Everything, little tiny lungfish, tooth plates, it's
Hmm.
extraordinary. And there hasn't been a lot of screen washing. I mean, the Mogollon Rim might be, a real target for some of these things because we
Yeah.
do get some fairly freshwater stuff, the Devonian and whatnot there that, have potential to produce diverse small stuff. But the later Paleozoic as well, Mississippi and whatnot, I told you about those neosalations I was finding at Peru. You're not going to find that stuff unless you look at the small teeth,
Hmm.
but the stuff is there.
So
And
when you're looking for an area to screen wash, what types of things are you looking for
we're
in?
looking for generally, like dirty beds, a little bit of plant debris, because there a buddy of mine has started blind screen washing road cuts of Cretaceous. And he'll just dig into these muds between big hard sand. He wants on breaks down,
Mhm.
And if it breaks down in water, the better, the simpler it breaks down, the better. So, those are, but you want things, oh, there's little mollusk fragments, snail opercula, plant scrap, some little clay clip, rip ups, so you want to get, we always joke, dirty, stuff, poorly sorted, but fine, mostly mud, so it'll break down.
Mhm.
It's hard to break down these hard cliff formers, but you get the beds in between and go for the little stuff, say, oh, can I use your screen boxes uh for forams and stuff to break them down. I developed a biostratigraphy with freshwater sharks or the lake Cretaceous of Western North America,
Mhm.
because hey, these things evolve. And certain taxa only occur in certain ranges. So if you've got, Pseudomyelodapus madsoni, you're in the upper Santonian,
Mhm.
in fresh water, so you can correlate it. These are, and you can correlate it from central Canada all the way to Mexico. I mean, there's, these things have utility, So
Yeah.
like, what are the utilities? I've been working on sharks, dinosaurs. We now have got the oldest, Cretaceous dinosaur faunas. And now I'm starting to think the northern hemisphere, for like multi-generic fauna beds. And we're showing that the Morrison style dinosaur faunas underwent a mass extinction at the end of the Jurassic.
Hmm.
You don't hear about a mass that killed off the Morrison fauna completely. And our stuff is mostly replaced by European taxa, apparently. We might have a couple of camptosaurs might go on, give rise to our iguanodonts, and or Mymorpelta might have given rise to polacanthines. But otherwise, it looks like almost 100% extinction of these things. And all the sauropods in North America go out. The megalosaurs, the allosaurids, ceratosaurs, they all go out. The big carnivores, top of the food chain, wiped out, completely. But so I've been researching, flood basalts and asteroid impacts. Just dive into, what does this mean? Develop your toolbox so you can pull out different tools that might be applicable, and then know who else is doing different things. Make friends with them geochemists. I
Yeah.
have a cadre of paleobiogeochemists that work with me. That's not what I do, but I know how much good stuff they can tell me about things.
Hmm.
And whether it's looking at oxygen isotopes and dinosaur teeth to track snowfall and the upland environments, or it's to look at carbon isotopes in fossil soils, to look at paleoclimate. All these are, various tools. I don't do that. I just know we got the stuff. Let's see if we find someone, so, be well read. And the internet, is priceless in that regard.
Yeah, that's
You
one of the
know,
biggest benefits for me and my generation is that with all of my paleontology knowledge, all of it is self-taught by just reading publications like yours or like David Ward or JP Honnett, all of these different people that I could just access on my phone or on my computer or anything. I can just read and basically obtain the knowledge that people that didn't have the internet took decades and centuries of time just like stacking all of this information onto itself.
Yeah, and being aware of, okay, these are dead ends, and people
Yeah.
stuck, having these old terms for things, just kind of drives me nuts, but
Yeah.
it's, we're building we're all climbing on the shoulders of those before us.
Hmm.
And and treat those before you well, say, okay, they made mistakes. You're gonna be making mistakes too.
Yeah.
Don't be the one that said, well, they were complete idiots. How could they have missed this? Well, it's when you're, lower on that pile of shoulders, it's easier to miss things,
Hmm.
So, show respect to the people that came before you, and understand, okay, this is why they thought that. Clearly there's reason,
Hmm.
we've learned a lot of things. I mean, the whole Carcharodon, megalodon story, I think is great in that respect. Like we just had this total wrong thing. We're going on for a long time. Origin of whales, you know, oh, their ankles, on early legged whales are like hippos and pigs.
Hmm.
Oh, they didn't come from condylarths, because they want to make them come out of a carnivore.
Hmm.
They came out of much more of an omnivorous line, you
Hmm.
know. And you look at those groups, but just keep your toolbox, keep a lot of tools and play with different things. Keep your tools kind of sharp. They don't have to be all perfect. You don't have to be the world's expert on everything
Yeah.
by any means. You're never going to be, but you want to have some expertise in a variety of areas. So it's like,
Hmm.
oh, if you're going to be working in Mississippian sharks, you want to get familiar with that invertebrate fauna too, and some of the depositional environments of those rocks. So if you say, oh, this is a really different environment. Oh, this is an estuary. This is not open marine carbonate.
Yeah.
This is some estuarine environment. Oh, maybe I can screen wash this and fill out a fauna, that we didn't know we had before. It's, definitely get, into those geology classes. But
Hmm.
anyway, where do you want to go next?
So you were talking about the different controversies in the past, like for example, the Carcharodon, Carcharocles, all of that, those
Oh,
different
yeah.
controversies. So on my previous podcast in another series that I do called Gentlemen of the Corax, we talked briefly about a debate between the Nanotyrannus T-Rex, that whole debate. So I figured, who
Okay.
to
Cool.
ask
I know
than
a
you.
lot of the players on both sides of that one. You know, no, basically, I'm open. I'm thinking, you've heard of the dueling dinosaurs.
Yeah.
North Carolina is working on that. Opened up a dedicated lab to their work. They paid 10 million, I think, for the fossil and the fossils, and I think they put 10 million into this new lab facility before the public, that they're working on it. And they brought on some very good postdocs to
Hmm.
work on this stuff. Young, brilliant, hungry young paleontologists. But I'm starting to get rumor that Nanotyrannus is probably valid, but they're also juvenile T Rexes. So people, you can't call everything, small, Nanotyrannus.
Hmm.
That's like wrong. Things do grow from
Hmm.
smaller sizes. Dinosaurs hatch from eggs no bigger than this, and then they go through all these different size ranges. But Nanotyrannus proper might be something that, with bigger forelimbs than Tyrannosaurus, and it's hard to come onto genetically. Okay, how do we shrink the forelimbs?
Yeah.
You can shrink individual bones, but to do the entire forelimb, say, okay, we're gonna, like get rid of the tail of a tadpole. Yeah, well, we're asking a lot, this stuff. And the little Tyrannosauroid has got some characters, as I understand it, that are, hard to, go into the big one without some real convolutions,
Hmm.
but some of these small animals have been called Tyrann. And is it the same as what was named Nanotyrannus? You get that's a skull pretty much by itself. So they don't have four limbs for that thing. Is that skull, a juvenile Tyrannosaurus? And then there is another animal that in the same size range is superficially a pretty similar skull, but there's anatomical features of its postcranial skeleton that show that it's not likely that it could grow up into a T-Rex. There's still a lot of questions to be answered, but I would keep an open mind. I think getting on, the flagship Tyrannosaurus Rex, and without any possibility of anything else, is not a viable ship to get on. But obviously Tyrannosaurus was the dominant large predator in North America, and there should be, more small ones than big ones. So if there's a smaller meat eater, a tyrannosauroid in the fauna, it's certainly not as common as the juveniles that are flying right through it, where this thing might stay that size for a long time, for decades, because it grows to that size and then stops. So hey, there's a lot to work on, but I've been hearing enough that I'm not going to say absolutely one way or another. And then how many Tyrannosaurus species are there?
Mm-hmm.
It's like, now we have another species in New Mexico that most people are really comfortable with. Is there a second species in the Lance Hell Creek? We have two Triceratops, Porosus and Herodus. A little lower down, you get Eotriceratops. So you've got, maybe anagenesis for that line. So is there another, Tyrannosaurus regalis, that's in a different level? I think regalis is actually above the type of Rex. So Rex might be the older. If there is, evolution in that line, that's significant enough that over millions of years, we shouldn't call it all Rex. Those are questions that, they'll be fighting about that in decades still, I'm sure. But we're getting a good collection of those materials, so they're resolvable questions. And there'll be new approaches, that'll be invented. People say, oh, we can start looking at this, and this can give us a better handle on ontogeny and how these animals change, something we're not even looking at today, because this is how the science progresses. We get new tools in our toolbox. Oxygen and carbon isotopes, stable isotopes. I took some of the first courses, they were just starting to get into that stuff when I was a grad student. And now, they apply this stuff to all kinds of things, and it's very significant what can be done. And we're still finding, new ways to tease information out of those isotopes in terms of how they work and how they work in different organisms. Different organisms, plant carbon versus soil carbon, or tooth carbon, all can, operate differently. Is this a phosphate versus a carbonate? They tell us different stories. It's neat. I mean, definitely keep an open mind. Pay attention to what people are doing, and don't hesitate to email people. Oh, I kind of like what you're doing. Can I come join your camp? You need a volunteer. Jump on board with folks. Because there's opportunities. But the tyrannosaurs, there are people that will die on that hill. I mean, there's no way I'm going to die on that hill. I don't work at tyrannosaurs. It's like there's plenty of tyrannosaur workers out there. They don't need me. Even the raptor hill, I got a Utah raptor under my belt, a couple of new ones coming along. It's like, you don't want to get too there, but we're bringing in this guy from he's now in New York, Stony Brook. Is actually postdoc is working on that in Tyrannus. They're dueling dinosaurs. But I basically told him, as far as I'm concerned, the Utah raptor block, you're in charge. because by the time we're really ready to do that stuff, I'm gonna be retired. I'll
Hmm.
be in my walker, at that point. It's gonna take some time, I'm 70 years old. There's, no more 25-year projects for me. Cedar Mountain stuff that was a good 25-year project, and I'm still doing little spin-off projects from it. There's other 25-year projects within it, but
Hmm.
I'm not in a position to, delve into something that's going to take that much legwork. You always got to, what's feasible to do, but you want to dig local, think global.
Yeah. And what's
It's,
one thing that you would love to see figured out in your lifetime as far as anything paleo?
oh man, well, I'd like to figure out what killed off our Morrison dinosaurs. No question about it. I mean, all I've done is say, like, yeah, the Morrison dinosaurs underwent that style fauna, because the end of the Jurassic, that record's actually in Spain and Portugal, where it's best developed. Most places in North America, we have an unconformity there. We're missing the last few million years of the Jurassic. They might be in Cimarron County, Oklahoma, maybe, parts of the Denver Basin, but the dating, we're not sure. I have a feeling that those giant latest Morrison things to the east may represent the end of the Jurassic. Things get big and get kicked off by an event. They have less room to evolve out of it. So the smaller animals end up taking over. But we don't have the dates. Those I'd love to know that. So I'd love to know what age is Cimarron County, Oklahoma. Those faunas, Saurphaganax. They've got like a 90-foot apatosaurus in those beds. It's like, what's the age of that stuff? Is that distinctive? Cope's nipple, in Garden Park, is that like Tithonian, this latest Jurassic? You've got Camarasaurus, what is it, Grandis, I think is the big giant Camarasaur. You got these big animals, is Amphisilus fragilis or fragilis, or how you say the species name. That thing is supposed to be like 180 feet long.
Hmm.
My take on that is it's part of a giant sauropod sacrum fragment that Cope misinterpreted as a single vertebra, just because of the way it was preserved and collected and sent to him. And then Cope later figured out what it was after he published it as a giant dorsal vertebra. Said, "Whoops, this makes me look stupid," and got rid of the specimen. Dumped it, buried it in the desert. Buried it somewhere in Philadelphia. And because he didn't want anyone to realize he screwed up. Because putting Elasmosaurus's head on the wrong end, he got a lot of grief for that over the years. And big egos, you can't be, I don't want anyone to prove me wrong. So,
Hmm.
I wonder if Cope actually got rid of the evidence, because that fossil's gone. People declaring this thing as this incredibly giant animal, bigger than anything known anywhere, based on drawings,
Hmm.
in a paper. But there is no fossil. There's nothing you can look at. Is that thing real? I have my doubts it's real at all. I think it might be that's completely misinterpreted. Pelvis. Heck, I misinterpreted a sauropod pelvis, thought it was a cervical vertebra, and I thought we had this gigantic apatosaurus.
Hmm.
But that's an apatosaurus sacrum. It's not the cervical vertebra.
It
Uh,
reminds me, Doug Wolf was talking to me about the Nothronicus bone that.
oh yeah, that one. Oh man. Yeah, Brenda Chenery was like, she wanted us to make that the holotype. That's ischium. The holotype is Uniceratops. And I'm like, I said, that's one bone. It's real weird. It's like unlike any ceratopsian bone I've ever seen. And to think that might be the squamosal. There's a life reconstruction of that animal that as its squamosal that was made.
Yeah, he
You know,
showed it.
yeah, yeah. It's like, I don't know. Doug, I think we should use the one that Christopher found, that has parts from throughout the body. It's a smaller animal. It's a little bit scrappier preservation, but we have jaw for, sections. We have teeth, we have pelvic, shoulder blade stuff. We have vertebra. We had a variety of elements, so we could better define them, all, certainly from one individual. So let's make that the holotype, and let's wait on that, because we described it in the paper as being part of the Zuniceratops. But dang, at least we didn't make it the holotype. Because as soon as I was working on my lab, we were preparing the material from that core in our lab, and there was this vertebra that was being prepped. I'm looking at it, and holy cow, is that a therizinosaur cervical vertebra? And and there'd only been like one picture, that's one of those, ever published, and it was by a paper by Dale Russell, and it was of the whole skeleton of this thing, Alexosaurus from Mongolia, or from China. And I'm looking at that, and I don't know why my bell rang. Therizinosaurus, because this is the first Therizinosaur in North America, so it wasn't something we think about. It's, oh, that's a possibility,
Yeah.
and, man, a Therizinosaur. And I'm looking at Therizinosaur stuff and say, man, that vertebra looks really good. And I'm looking at other papers and that bone looks a lot like an ischium, the Segnosaurus, and I brought it to the meeting, a week later, it's like the paper hadn't come out yet, it was in press, we couldn't change it. And I showed it Jim Clark, George Washington University, and Jim's like, yep, that's a Therizinosaur ischium. I had a replica, a cast. It just, whoa, okay. But Brenda, who was a ceratopsian person, more so than me at the time, it was like, oh, you should make that the holotype, because it's a very odd bone. And we were finding a lot of ceratopsian stuff of a very odd ceratopsian, so it's but yeah, if the holotype of Zuniceratops had been Nothronicus, we would have had a therizinosaur called Zuniceratops. So skin of our teeth. That's how science works. You got to be careful. Publishing. I named Utahraptor initially on the big sickle claw that we had. Now we know everything from that quarry came from one animal. So we have vertebra and other skull, premaxillas and post-orbital and ribs and tibia. We got a variety of bones from that animal. Stragulus. So you put it all together, and we got a reasonable hypodime. Which is the things we can define that taxon, which allows us to look at other overlapping specimens, because a lot of dinosaurs aren't complete. So you've got to be careful. And I'm working on naming a number of new armored dinosaurs, and it's like, okay, I've got 3 animals in this quarry, and one that's pretty good size, and 2 that seem to be more juvenile sized animals. The basal crania, both from the juveniles, actually, and they're from another place in the quarry, so we might actually have 5 animals. But I have 2 basal crania that are pretty small, and are distinctive. But that could be a completely different animal. So do I use the pelvis? Do I, and what I'll probably do is a combination of the largest elements to say, okay, the hypodime, we think these are all from one animal. And, and I think all of them are from the same species, but you never know. That's kind of what we're thinking with Zuniceratops. We're like, oh, this is a ceratopsian bone bed. And there was, we knew we had a meat-eating dinosaur pedal claw in there, and the time was it later, Andrew McDonald thought it was a tyrannosaur. He wanted to describe it as a tyrannosaur claw. We now know that's a walking claw for Nothronicus. So it wasn't a tyrannosaur either for that one. So you gotta be careful, but I've been fortunate. I haven't stepped off any gigantic cliffs. I haven't had any. We got an animal I was co-author on. This guy, Phil Center, was the lead author, describing this maxilla as a troodont.
Hmm.
And it turns out it's another therizinosaur. The lower Cedar Mountain, the yellow cap member of the Cedar Mountain Formation now has pretty convinced 4 different genera of therizinosaur in one unit.
That's
Unit represents like 15 million years, but you say the basal Cretaceous is kind of like the age of therizinosaurs and coelacanthines and pterosaurs. It's a very distinctive assemblage of beasts, but yeah, 4 therizinosaur taxa.
That's crazy because it kind of shows how science can go so fast because up until Northern-Icus, we didn't know of any
Any,
North
yeah.
American
Yeah.
therizinosaurs. Now
And I
we
think Northern-Icus came in on a separate immigration event.
Mhm.
I think, all these 4 that were, saying the yellow cat, I do think they went extinct, in the early Cretaceous at some point. Maybe at the end of Wealden time, but maybe at the end of yellow cat deposition or
Mhm.
poison strip deposition. I mean, there's so much more to learn. We figured out a lot of stuff from these rocks because there were only 2 dinosaurs known from it before I started working. And, now we have like 70 species in those rocks, and it's 45 million years. It represents a big chunk of
Yeah.
time. So, having a lot of taxa, the Morrison, is like 7 million years, so it's not nearly as much time, and we've got a lot of dinosaurs there because we've really worked on it. And it's very diverse prior to a mass extinction. But yeah, there's a lot to learn in these rocks and all this stuff. It's not like it's all been done,
Mhm.
so, be, I got, screwed over. There's no other way to point it. I was the first one to identify the tidal wave deposit at the KT boundary in Texas.
Mhm.
Brazos outlined the whole scenario for what happened. Only thing I couldn't figure out is in the basal rubble bed, how they've got angular, unconsolidated clay class. I mean, like clay, rubbery clay, that angular. And how we get that? Because most of the stuff we're seeing, like concretions and all these shark teeth and glauconite,
Mhm.
broken up, mollusk shells, broken up ammonites, that's all being ground up as the tidal wave came across the shelf. But, how'd you get angular clay? That shit all been rounded, braided, or there. My only thing was maybe there's like, shelf channels, going across the shelf and they broke off the edges. And their scenario when they published, and I'm not credited even to helping in that paper at all, they basically said my entire scenario, point for point, except the clay class in the rubble bed, the tidal wave hit the continental shelf edge, Texas shelf edge, and
Mhm.
across the Gulf, the Proto Gulf. So it wasn't as wide, but still there was deep oceanic, water there. That huge wave, that was at that point half a mile high,
Mhm.
hit that continental shelf edge like a seawall and just ripped the edge up right out over the shelf. And that explains those things. It just, unconsolidated, just peeled it back
Mhm.
as it hit the Texas shelf margin, and it makes total sense. I'm like, yeah, that's it. That's what happened. But otherwise, it's all my scenario. I got zero credit.
Mhm.
And what I find comic is those guys never followed up. And like within a year, oh, what's the guy's name? He's from Arizona, University of Arizona. Um, I always space his name, but him and his advisor, he was a grad student at U of A. He started running around the Caribbean looking for more tidal wave deposits. And on Haiti, found a half a meter thick tidal wave deposit with part of the ejecta blanket, with like, you know, decimeters of tektites,
Mhm.
just roll them out, all this molten glass from the impact, in Haiti. So he published a paper that the impact definitely happened in the Caribbean region, probably within 100 miles of Haiti. And he speculated that there was a structure off the coast of Colombia that he thought could be the impact. And
Mm-hmm.
then within the year, the folks in Mexico that were working on the Golden Lane, the cores that had first proposed an asteroid impact at Chuluxpub in 78 and were just laughed at by they worked for the oil company there. Not his. In 81, they were given permission to present a paper at the International Conference of Geophysicists. And they presented, but in 81, which was a year after Alvarez proposed extraterrestrial, extinction, cause for the dinosaurs, they had a conference in Snowbird, Utah, and everybody with any knowledge about asteroid impacts and things interested in the KT boundary are all in Snowbird, Utah, the exact same week that these guys presented at this geophysics conference, where no one really cared anything about dinosaurs or meteors. They're all petroleum geophysics types,
Mm-hmm.
so they just got just swamped until 1990. And they saw this paper and they said, oh, we got to talk to him. And immediately they tracked down this core that was in a warehouse in New Orleans and found impact shock quartz and all the stuff from a core that went right through the crater. So this is ground zero, and we're able to prove it, and it dates just where we want it. Got the ejecta blanket, but the group, I was a grad student. I was a grad student. I was working on a PhD at the time, but I was hired as help to identify fossils in that section and look for ecological changes before the boundary. Things are probably slowly dying out. What's going on? Nothing changed right to the tidal wave. Basically those guys never followed up, which would have been the most logic thing in the world, but later they went down to Mexico and I ended up doing a lot of work in Mexico, this place Canyon El Barril, and said, oh, the impact is here at the top in the basal Las Imagines formation of the De Fuente group above the Serra Grande, which is a big Maastrichtian marine sequence.
Mm-hmm.
And basically it was a little clay parting in this beach sequence. Well, as it turns out, the sea came in again because we're right down by the edge of the continent there. And there are pterosaur bones, ammonites, way above where they were gonna publish that was the boundary. And that, we haven't found the iridium yet, but that clay layer right there has got to be it. And they were in a big, huge delta sequence. So they had all this convolute bedding, pro delta. You get these, slump structures, and that's what they were saying. Mud lumps like we had the Mississippi, and they thought, oh, this is because of the impact, and crag coming in, like total, they didn't have a clue. Yeah. And we got a schizorrhiza up there in the Rancho Nuevo formation, well above them, with this other stuff. And that's in my paper on schizorrhiza. I got a picture of that too. So, here's a Maastrichtian, taxa that it's not like at a nonconformity. We got a lot of this stuff. The KT boundary in Texas, that shark lag winnowed down as the shelf eroded. This one's up in, the right habitat that this thing probably was living. And of course, PMEX guys that were with us, they got ammonites up there too. And further up section, there's some glauconite beds. And that's where I think the impact is. These big glauconite beds in like the middle third of the way up the Rancho Nuevo. And that's where I think we have the impact, there in the La Polpa Basin. But took a field trip out there in 2000, show them dinosaur sites and stuff. I was the expert then on the dinos. And said, I think this is the boundary. And, and I think it's pretty close. But there's a lot more work in Mexico to do. And they had a theory that, the Arctic might have been kind of landlocked for a while. And all of a sudden you opened up part of the North Atlantic and a very fresh Arctic water mass came in and flooded over the surface of the oceans, killing off all the plankton. Didn't happen. But that was a theory that came out, because a lot of other people thought, what did the plankton in could have caused a chain reaction that did everybody, across the thing. But what we've got, this asteroid that hit The Mauritian impact in South Africa, the end of the Jurassic, that hit crystalline continental rock right in the middle of the continent.
Mm-hmm.
So, Chicxulub hit a barrier reef, like the Great Barrier Reef. It's a rudisted reef system, but a big carbonate reef system with all these evaporite sulfates on the landward side lagoons. It was very, and down in the subtropics, getting into more arid belt, because I'd work on dinosaurs down there, so it's definitely, a lot drier than the Lance is and stuff up here. And so you had all these sulfates down there. And figure if you took over a 100-mile stretch of the Great Barrier Reef with a big evaporite sequence behind it, and basically vaporized the entire thing.
Mm-hmm.
And it's probably almost a mile thick, or at least half a mile thick of carbonate, and you vaporized it in the atmosphere, and probably about a half a mile thick, maybe a bit less of sulfate, sulfur rain, acid rain, vaporized it into the atmosphere. Create these tidal waves, and all the, tektites coming up, starting forest fires over thousands of square mile areas around. I mean, that impact, because of where it hit, because the one in South Africa is about as big a crater, did not have nearly the same, effect that the one at the end of the Cretaceous. And I think it was where it hit is what really, you completely screwed up the planet's atmosphere for a period of time. Because the one that hit in Africa would send up the dust clouds, we would have nuclear winter, all the same stuff. But we would not have saturated the atmosphere with carbon, calcium, carbon dioxide, saturated it with sulfur dioxide, at a level that it hadn't seen probably since the Paleozoic, and big events in there. It was a big deal. Freshwater mollusks, all the complicated ones, only a few simple forms of unionid survived. A huge number of terrestrial plants went extinct. Mollusks, gastropods, flutomorphic gastropods. There's types of velutids that have planktonic larval stages, others that lay eggs on the seafloor and crawl away. The ones with planktonic larval stages decimated. The reason ammonites went out because they did this tiny little, planktonic stage in their life. They were nautiloids, got big eggs, and they hatch and start swimming immediately. Ammonites, anything that was in the plankton, decimated. So the whole chain reacting through marine ecosystems. Incredible. All the mosasaurs and last, they were doing good at the end. All went out. Basically, for like plankton, the foraminifera stuff. Some of these things like the coccolus and whatnot. You could think, a handful survived, and then gave rise to the plankton later because they reproduce like every couple hours. Coccolus, diatoms. These things reproduce fast. Dinoflagellates only been under like 50% extinction, but they can insist. So things are bad, and they just form a cyst and wait it out. And a lot of dinoflagellates can do that. So dinoflagellates as a phytoplankton didn't get hit nearly as hard. But coccolus got nailed. Remember, it was Cretaceous chalk. It's coccolus, the age of chalk, decimated. It's really incredible when you think about how bad that extinction was across the board. It was nearly as bad as the Permo-Triassic extinction. With the estuarine ecosystems, if they reproduced up in estuaries, they probably had a good shot of making it. Brackish water stuff barely got touched. Why is that? And a lot of the freshwater aquatics didn't get touched too much overall. And that's because detritus from all the dead stuff going in supports bacteria and fungi and stuff. So you can have what we call a brown food chain. Estuarine environments, very much so. Where it got, decimated the worst, tree-based, terrestrial plant-based ecosystems and marine plankton-based ecosystems. But the stuff that like the the muddy ponds and estuaries, where things are mixing and salinity fluctuates and oxygen levels can fluctuate. They're already pre-adapted to stress.
Hmm.
The things that were in those systems, crocodilians, a lot of turtles, certain, fish that, sharks that probably reproduced in those settings. They could take advantage of the brown ecosystem to find food.
So
Those
maybe
things made it.
so maybe if Spinosaurs lived up until the Maastrichtian, they could have survived too.
Well, yeah, but they're
Easy to
eating,
think
big
about.
stuff,
Yeah.
tops of food chains. Crocodilians did it though, but where
Mm-hmm.
they, Dinosuchus did, and the giant crocs didn't
Mm-hmm.
make it across. How big were the crocs that survived it? You know,
Mm-hmm.
there's as I say, a lot more research to be done.
Yeah.
But we're trying to get a better handle on this stuff. But it's everyone's so focused on dinosaurs or ammonites. I love ammonites, but there's a lot more going on than just a few taxa.
Mm-hmm.
I mean, freshwater mollusks and the degree of things that went out, and we start looking at, okay, who survived and where did they survive, and freshwater aquatics, and elasmobranchs reproduce slowly. Even
Mm-hmm.
in freshwater, those things weren't reproducing like bony fish were, and but crocs survived, champsosaurus survived, a number of the turtle groups survived, and even the turtle groups that went extinct in the tertiary made it,
Mm-hmm.
made it across the boundary. Mammals, marsupials almost went extinct. There's only a couple marsupial groups that survived through that boundary. A number of placental mammal groups didn't make it through. I mean, people say, oh, mammals didn't make it through. When they look, Bill Clemens at Berkeley did this great study where he looked at each faunal level, starting, like way down to the base of the Campanian, up through the upper Campanian, Maastrichtian, into the Paleocene, the Paleogene. I looked at the micro, the mammal faunas and said, okay, at this level, so many critters, which critters survive through this to the next level, which ones go extinct but might have evolved into another taxa upsection, and which are new ones that came in that, are, immigrants,
Mm-hmm.
and you go and do that. The end of the Cretaceous, almost nothing made it through, and almost all the mammals above are immigrants elsewhere.
Mm-hmm.
They're not things that evolved in place for the most part, even though there's sometimes they're members of the same lines, but they were probably coming out of Asian taxa, things like that. So we look through that classic, sequence where they have great microsites going through the entire thing.
Mm-hmm.
It's like mammals, the bulk of them, are replaced by related immigrants and not by things that evolved and lived through the boundary.
Mm-hmm.
So you always say, "Oh, mammals made through. We did it because we're tougher and we're smarter." It's like, yeah, birds. 90% of all bird groups in orthines, which are the dominant bird right to the end of the Cretaceous, in orthines, totally extinct. The odontiform means all the tooth birds, of the ornithine birds, ornithurian birds, how you say modern bird group, they all went extinct. It's probably a handful of terrestrial birds that happen to be of our modern, give rise to all modern birds, made it through the boundary. I mean, it's, Bacher used to always scream, what about the frogs? There's like one frog taxa known in the late Cretaceous, maybe two, because frog taxonomy, you say, well, we're looking at, frog, sacral bones. I mean, frog taxonomy at any kind of deep level is not based on their skeletons.
Mm-hmm.
There are differences, but but a lot of frogs, like poison dart frogs, incredibly diverse, but it's all color patterns and songs and stuff. Their skeletons are virtually identical. A lot of lizard groups, if it's skeletally different, you can tell the skeletons apart. It's a different genus.
Mm-hmm.
Species of lizards is generally color patterns and stuff.
Mm-hmm.
Details of scale patterns. And that's we're missing all that stuff in the rock record.
Yeah.
We just once again, like with sharks, we got to be real careful. What are we looking? What's the basis of our taxonomy? And
Mm-hmm.
is it biologically really sound? And for some of those groups, biologically, it's not sound at all. In terms of what mass extinctions.
Mm-hmm. And
But
As like a closing off conversation, do you think we will ever find a Paleocene non-avian dinosaur fossil?
I seriously doubt it. Yeah, I seriously doubt it. Because the crisis wasn't like a couple of years. That was probably hundreds to maybe even thousands of years of, the Earth probably had a ring around it. We probably had a ring around it after the Jurassic one. In fact, that was a big impact. Uh, but clearing out the atmosphere, bringing it to normal, changing, you always see like the Z coal, the coals right above the boundary. We see the same thing with the Jurassic. We got this real wet interval right after the extinction. And it goes away and then it goes back to similar climates as the Jurassic. But this real wet interval, what is that based on? What is going on in our atmosphere for that time? But it's, we're looking at, for the end of the basal Cretaceous, into the Jurassic, we have multiple soil horizons showing the change in climate back to what it was normally. That took thousands of years. So that perturbation in the Cretaceous, same way, you shift into coals immediately. And the planet gets really warm. Paleocene's a pretty warm time interval, even compared to late Cretaceous. The effect of what happened is remarkable. It kept up because we have this big volcanic center south in India, the Deccan Traps. They were going off for millions of years before the extinction, and may have had an effect, on animals. Big, gigantic, the end of the Permian might be mostly the Siberian traps, or that with an impact that we're missing totally, that was subducted. But we don't see the extraterrestrial signature for the end of the Permian. The end of the Triassic. It's also probably the camp, the Central Atlantic magmatic province probably did in the end of the Triassic. So there's more than one way to kill a bunch of dinosaurs.
Yeah.
We always keep that in mind. But asteroids are one of them, and asteroids do come barreling in periodically. And for some like Ogajava, that might be, it's a huge flood basalt. They think it's the biggest one there is, big area of flood basalts, but it's in the Southwest Pacific. And it's been kind of ripped apart by plate tectonics. When they pull it all together, it's gigantic. But that huge area of flood basalts, so it forms a kind of a ring. People have proposed that that might be an asteroid impact for the end of the Birimian extinction, before we go into the Aptian faunas. Could have happened in the early Aptian as well. But this impact was an asteroid going through oceanic crust, which is only like 10 miles thick. And, remember the crater it's loose above is 30 miles deep. If that hit oceanic crust, it would have just blown on through into the mantle. And if that happened in this thing in the Southwest Pacific, it wouldn't put all that salt in the air, all that carbon dioxide. It would have had effects. There's just all this lava came up. And there is a big faunal turnover at that level. But its effect wouldn't be nearly as bad as hitting that coastline with that barrier reef, sitting on it. But that might, there's two scenarios. Is it just, hotspot, basalt, or is there an asteroid that blew on right through the oceanic crust? And that might have happened more than once on the marine basalt plateaus. More than one of those might be an asteroid impact. That just once it happened, just flood basalts come up and bury it all. We got a lot to learn still. We know a lot more than when I was a student. We've learned amazing things since I started off. Plate tectonics was just coming into its own, and I knew people didn't believe in it at all when I was a student starting in. Didn't believe in plate tectonics. Think now, you are a flake if you don't believe in it now. But when I started off, that was a pretty new theory coming up in the 50s and 60s. A lot of people didn't believe it, and that's, this fact that the Earth is part of our solar system, and there may be, a greater part of our local solar system activity, the sun fluctuating solar output. Maybe there's things that burps on the sun that could have big effects. There's a lot to learn, and we're learning it. We got, some things targeted, but we have big things that we don't know what happened.
Hmm.
Was there an asteroid impact at the end of the ice age? There are people that believe that. I think the data is just totally in the air. Human cause, did we kill the megafauna? Or, was there a big impact, or a comet that exploded in the atmosphere? We're certainly not there with that one, one way or another. Um, or is it neither? you know, and there's stuff. Keep going. There's stuff for you to do,
I
at
appreciate
all
it.
levels, in all areas, which is the fun part of this stuff. Don't ever think the work is done. It'll
Yeah.
never be done.
Well, thank you so much, Jim, for joining us. I think that the audience will really love this conversation. Um, for anybody watching till the end, you clearly love this paleontology stuff. So feel free to like, comment, subscribe. But yeah, thank you everyone for tuning into Elasmocast. We'll catch you guys next time.
It's been fun.
It has.